There we go. All right, so here are the basic identities, and you should already have these in your notes from our unit circle conversation a week or two ago. So what we're going to do is I'm going to show you how to use these identities in different ways. The first thing we're going to do is actually find numerical values using these identities. And then the second thing we're going to do today is we're going to simplify trig expressions, okay? Which leads into what we do next week, which is verifying and some difference formulas. So make sure that you are looking at these identities. So it says to find a trig value with identities, use the quotient and reciprocal identities to find each function. So the first thing I'm doing is I'm looking that they've given me secant, and then they asked me to find cosine. Well, if you notice up here, secant and cosine are reciprocals of each other. So when that happens, all I have to do is take this number and flip it. That's what a reciprocal is to turn a number upside down. So if I have secant and it's reciprocal, then I'm going to flip that, and it's going to be -3 over square root of 30. You do have to rationalize that, so we do have to multiply by square root 30 over square root 30. And that gives me -3 square roots of 30 over 30. Final step, reduce the 3 and the 30. So that gives me negative square root 30 all over 10. And that would be the cosine value. All right, so if you have reciprocals, use them. Take the fact that secant and cosine are reciprocals, take secant, flip it, and rationalize it. Now, when I look at these properties, I don't see a direct relationship from tangent to cosine to sine. But what I do see is this property right here that kind of relates all three of them together. Tangent is sine over cosine. So I'm going to use that property, and I'm going to do a whole lot of math. So tangent x equals to sine x over cosine x. That's the formula or identity that I just pulled from the list. So I'm going to put tangent in, that's square root 2 over 4, equals to sine x, because that's what we're solving for, over -2 square roots of 2 over 3. Everybody okay with those substitutions so far? I'm just picking a formula that tries to relate everything together. Okay. Now I have to clean this up because my final answer needs to be sine x equals to something. So what is sine x going to equal to? How do we do the math to clean this up? Well, you have a fraction equal to a fraction. Do you agree? So you can cross multiply. So it's square root 2 times this whole denominator, -2 square roots of 2 over 3, and then 4 times sine x. When I multiply here, I actually end up with -4/3. What happens is if you take the square root of 2 and put it over 1 and multiply that by -2 square roots of 2 over 3, you get -2 square roots of 4 over 3. What's the square root of 4? 2. And 2 times -2 gives me -4. So that's where I got this number from. Now, one final thing. Divide both sides by 4. So what does sine x actually end up equaling to? I need the exact value, not a rounded decimal. So what is -4/3 divided by 4? Is that what you got? -1/3? Okay. Now, Number 3 doesn't directly relate cosecant to cotangent to find secant, okay? But what I can do is I can use the fact that cotangent is equal to cosine over sine. Now, the reason I'm choosing that one is because cosecant's reciprocal is sine and secant's reciprocal is cosine. So if I can use that information and figure out what cosine is, I can flip it and it gives me secant. So what I'm going to do first and foremost, I'm going to change that to sine beta, which means I'm going to take 7 over 3 and I'm going to flip it. Then I'm going to plug the numbers that I know into that identity that I chose. So cotangent beta is negative 2 square roots of 10 over 3 equals to cosine beta over 3/7. And once I figure out what cosine is, do not forget to go back and flip it because you need the reciprocal. You're actually solving for secant, cosine's reciprocal. So I'm going to cross multiply. So negative 2 square roots of 10 times 3 over 7 equals to 3 times cosine of beta. Here I get negative 6 square roots of 10 over 7 when I do the math. And then divide by 3. I get cosine beta equals to negative 2 square roots of 10 over 7. When you divide both sides by 3. Everybody okay with that so far? I got to cosine in order to calculate secant. Secant is cosine's reciprocal, so I'm going to flip this and clean it up. So I get negative 7 over 2 square roots of 10. Rationalize that denominator by multiplying by the square root of 10 over square root of 10. That gives you negative 7 square roots of 10 over 20. That would be the value for secant. So sometimes they give you a direct relationship, kind of like secant and cosecant being reciprocals. They are directly related. Sometimes they give you another direct relationship because tangent, cosine, and sine are relatable via that identity, but sometimes they don't. So you have to be on the lookout for when they don't, okay? There's not a direct relationship, but there is an indirect relationship by using the reciprocals and things like that. So be very careful. All right, now we pick up 3 more identities. You pick up your Pythagorean identities. So some of the problems that we just worked, we could have used the Pythagorean identities for, but they want you to kind of play around with all these substitutions and things like that. So in this particular problem, I need to find cosine and tangent if they give me the fact that sine is negative 1/3 and cotangent of theta is less than 0. Now, we're going to take a side note for just a second. We talked about this briefly. We didn't spend a whole lot of time on it. But when you are on the unit circle, this is, of course, quadrant 1, quadrant 2, 3, and 4. All 6 functions, all 6 trig functions are positive in the first quadrant because your x and your y value. Are there any negative values in quadrant 1? No. So nothing no y over x or x over y or x or y can be negative. Okay, so sine, cosine, tangent, and all the reciprocals. If you have an angle that terminates in quadrant 1, all 6 trig functions have positive outcomes. Does that make sense? Now in the second quadrant, there are only 2, because in the second quadrant you have negative x, but you have positive y. So out of the 4 trig functions, there are only 2 that are positive. The positive functions for quadrant 2 are sine and its reciprocal cosecant. That means tangent. If you have an angle that terminates in quadrant 2, tangent will be negative, cotangent will be negative, cosine's negative, secant is negative. Makes sense? Third quadrant. Every ordered pair in the third quadrant, negative x, negative y. There's only 2 positive functions in the third quadrant. That's tangent and its reciprocal, cotangent. In the fourth quadrant, you have a positive x coordinate and a negative y coordinate. What's the only function we haven't listed yet? Okay, so secant and its reciprocal, cosine. So cosine and secant are the positive trig functions in quadrant 4. That means sine, tangent, and both of their reciprocals will always be negative. Why does that work? Well, if you go back to unit circle, the sine value is y. Y is negative here, it's negative here, but it's not negative here. So sine will be positive in the first and second quadrant always, negative in the second and third. Tangent, go back, is y over x. You put a positive over a positive, it stays positive. You put a positive over a negative, it turns into a negative. All 6 trig functions are positive. When you get down to quadrant 3, you put a negative over a negative, it turns into a positive. So that is why when you are in certain quadrants, certain functions are positive and certain functions are negative. Now, just like please excuse my dear Aunt Sally, there's a little saying that goes with it. All students take calculus. Okay? All students take calculus. The A stands for all. All 6 trig functions are positive. The S stands for sine and its reciprocal. T stands for tangent. And C stands for cosine and its reciprocal. So all students take calculus. That's a way that you can kind of remember which functions are positive in what quadrant. The reason I'm telling you this is because I need to know that for this particular problem and this particular problem. Okay, so we're asked to find cosine and tangent if sine is negative 1/3 and cotangent is also negative. So out of the 4 quadrants, which 2 can produce a negative sine outcome? It's not first quadrant. Nothing's negative in the first quadrant. Third and fourth. Okay. Now, out of those 2, there's only one place that cotangent is negative. Which one? 4. Because tangent and cotangent are always positive in quadrant 3. Ooh. Got a frog in my throat all of a sudden. All right, so what I'm going to do, the first thing I'm going to do to find cosine is I'm going to use the Pythagorean identity that relates sine and cosine directly to each other. And then the second thing I'm going to do is go back to one of my other identities, since I do have to find tangent, which says that tangent is equivalent to sine over cosine. So I have a lot of work that I have to do. So here they gave me sine is 1/3. So cosine squared theta plus negative 1/3 squared equals to 1. That's cosine squared theta plus 1/9 equals to 1. When you subtract 1/9, you get 8/9. And then we have to take the square root of that, and we get two answers, a positive and a negative. Anytime you apply the square root property, you get a positive and a negative outcome. Well, when I simplify the square root of 8/9, that's the square root of 8 divided by the square root of 9. The denominator is a 3. That part's easy. Square root of 9 is 3. We have to break this down. That would become 2 square roots of 2. So I get 2 square roots of 2 over 3. And then based on the fact that we are in quadrant 4, which one of these do I keep? The positive answer or the negative answer? What is cosine always going to be in quadrant 4, positive or negative? Positive. So I'm going to take out the negative. So there's cosine. They gave me sine. I now have cosine. I can use that to find tangent. So tangent is going to be my sine value that they gave me divided by the cosine value that we calculated. And then we have some math to do. I'm going to take negative 1/3 and multiply it by 3 over 2 square roots of 2. My 3's cancel. I end up with negative 1 over 2 square roots of 2. And then I have to rationalize that. So when I rationalize that, what will my final tangent answer be? Negative square root of 2 over 4. So I have both of the answers that they asked for. Now, before I say absolutely, is tangent supposed to be negative in quadrant 4? Okay, so all my answers make sense based on the initial quadrant that we were in. Number 5, these are my favorite. Because if secant is positive, secant is only positive in the first. Everything's positive in the first. And in the fourth, because cosine and secant are always positive in the fourth. Out of these two quadrants, which one is sine positive in? First one. So all things positive in the first, I don't need a single negative answer. Make sense? That's the relevance of this. This tells you what quadrant you should be in so that you know when you do the square root properties that you are finding the right values. All right. So first thing it asks us to find is tangent. If you look back up here, you have a direct relationship between tangent and secant. Do y'all agree? All right, so the first thing that I am going to do is I'm going to grab this formula, tangent square theta plus 1 equals to secant square theta. I'm going to replace secant with, I know it says x and I'm using theta, it's just a bad habit when I do trig. That would be 6 over 5 squared. So I get tangent square theta plus 1 equals to 36 over 25. When you subtract 1 from both sides, you should get 11 over 25. And here is the relevance, because right here, when I take the square root, technically I get two answers. I get a positive and a negative square root of 11 over 5. And based on the initial information, you have to decide, do I keep the positive because tangent is positive in 2 places and tangent is negative in 2 places? Since we're in quadrant 1, I'm going to keep the positive. All right, so tangent is out of the way. Now, I still have to find sine. Any thoughts? Any thoughts? I'm going to use tangent theta equals to sine theta over cosine theta. I have a tangent value. I'm looking for sine, and where do I pull the cosine value from? Secant. When I flip it, that becomes 5 over 6. All right, so now I have to clean this one up. I'm going to erase a little bit of the work from the previous problem so I can kind of come up here and do my work. So I'm going to multiply square root of 11. So that's 5 square roots of 11 over 6 equals to 5 sine. I'm going to divide both sides by 5. And that will give me my sine value. You should end up with square root of 11 over 6. Any questions about that? Everybody good? All right, so the last little bit on this particular page talks about cofunctions and even and odd functions. Cofunctions are the ones that add up to 90 degrees, such as if I gave you sine of 40 degrees, its cofunction would be cosine of 50 degrees. Sine and cosine are always cofunctions. These two measurements have to add up to 90. If you type both of those in degrees on your calculator, you are going to get the same exact decimal. Try it out. Did y'all get it? Same decimal? All right, so we're going to use the cofunctions and the even and odd identities. By the way, let me back up and talk about evens and odds. These two are considered even functions. The reason they are considered even functions is if you plug in cosine of negative theta, it will equal cosine at positive theta. okay? Such as if you type in cosine at negative 40 degrees, it will give you the same exact outcome as cosine at positive 40 degrees, okay? The other ones are considered odd. Because if you do that, notice that I have a negative in front of all those. When I did that here, when I plugged in a negative theta, I ended up with a positive outcome. But for these two, I ended up with all those negatives. So what we're going to do is we're going to use a combination of these cofunctions and evens or even and odds to figure out what these cofunctions are. Okay? So first thing I see is inverse sine. So the basic thing, I need cosine of pi over 2 and according or minus theta. So according to this, positive sine theta is equal to cosine of pi over 2 theta. Do y'all agree with that? So if I can figure out what sine theta is, both of those will equal to each other. So I'm now going to use my even and odd function. If sine negative theta is equal to negative sine theta, do y'all agree? Based on my function, and the value of sine negative theta is negative 0.97. Do y'all see what I did? I grabbed my formula and then I took this and I made the substitution. Y'all with me? How would you solve this for positive sine? Divide both sides by negative, right? So that's 0.97 equals 2 sine. Everybody okay with that so far? All right. Now, this was the goal, to get cosine pi over 2 minus theta. Well, cosine pi over 2 minus theta is equal to sine theta. What's sine theta? 0.97. So that would be my outcome. All right. In the second one, I need to find cotangent, and this is actually misprint. This should be pi over 2 minus alpha, so fix that on your paper. They had that backwards. So, according to my cofunctions, tangent alpha would be equal to cotangent pi over 2 minus alpha. Y'all agree? Doesn't matter if it's theta, alpha, x, it doesn't matter. Greek letter, English letter, does not matter. Okay, so that's the outcome. Well, they give me tangent of negative alpha, so I'm going to come up here and I'm going to grab this. I'm going to work through it. If tangent of negative alpha is equal to negative tangent alpha, that's the formula. I'm going to take this out and replace it with the value that it gave me. So negative 2.36 equals negative tangent alpha. Divide both sides by negative, so you have tangent alpha as 2.36. Since tangent alpha is equivalent to cotangent pi over 2 minus alpha, then cotangent pi over 2 minus alpha is 2.36. Everybody okay with that? Now, in the third and final example on this page, they're starting you with the cofunction and they want the odd function. So with respect to secant and cosecant, this is the function that I want. Cosecant beta is going to equal to secant pi over 2 minus beta. That's the cofunction. Everybody with me? Okay. Thoughts? What should I do? Actually, this one is wrong too. This one should be pi over 2 beta. I apologize. All right. Well, if secant of pi over 2 beta is equal to negative 3.62, cosecant of beta is equal to negative 3.62. But I don't want cosecant of beta. I want cosecant of negative beta. So, according to this statement right here, cosecant of negative beta would be equal to negative cosecant of beta. Do y'all agree? I have positive cosecant. What can I do real quick to make it negative? Multiply by negative 1. So that would give me negative cosecant beta equals to positive 3.62. And since negative cosecant beta is equal to cosecant of negative beta, then I have my value. Out of everything we do, I think these are some of the most confusing things. Did I just say that on video? I think I did. But it takes a while to get used to them because you have to go in multiple directions. We're always used to going from point A to point B. We don't like it when we have to go from point A to point C to point B, back to point A. Okay. All right. So that's the end of that. And now we're going to get into simplifying trig expressions. And this is a little bit different because when we solve these or simplify them, that means rewrite this whole expression as a numerical expression. Rewrite it as 1, rewrite it as 2, rewrite it as 29, a number, or in terms of a single trig function. Okay? Identities are useful in simplifying trig expressions. So we have 8, 9, we have 12 examples to go through. Okay? So over on the left-hand side, they've given us some strategies. Now, I am going to start by saying this. There is no one way to do any of these problems. The correct thing to do is make legitimate substitutions using the identities on the front cover of your packet. That's rule number 1. Make sure it's a legit identity. And then do the math right. When you add fractions, you have to have common denominators. Have you ever factored before? Have you ever FOILed before? Anything that you have ever done in math is about to come out with respect to trig functions, okay? So you have to stop and think about what you're doing, and you have to make sure the math is sound. All right, so some of the strategies that they give us over here, and I'm going to give through quite a few of these today. Rewrite using reciprocal and quotient identities, meaning I can rewrite secant as 1 over cosine. That's one of my reciprocal identities. Okay? Look for Pythagorean identities. The catch with the Pythagorean identities is you have to have squared quantities. A squared plus B squared equals C squared. Nowhere does the Pythagorean identity say A plus B equals C. It's A squared plus B squared equals C squared. So if you are using the Pythagorean identities, your values have to be squared. Combine fractions by using a common denominator. That's how you've always added fractions, found a common denominator. Break fractions apart. This one's a little bit different. When you break fractions apart, you want to make sure that they have monomial denominators. So if you had A plus B over the monomial C, monomial, not binomial, you have to do something totally different when your denominator is a binomial. You can break this up into A over C plus B over C. Now, normally we start here and we end up with a whole fraction. Do y'all agree? But sometimes we're going to have to break those up. But you want your denominator to be a monomial in order for this to work right. Then, of course, the last bullet says use factoring. Difference of squares, factoring quadratics, all of that stuff will come into play at some point. All right. So in this particular problem, I'm going to show you when all else fails, turn everything to sines and cosines. Everything has a sine and or cosine equivalent. So secant is the same as 1 over cosine. Sine, I'm just going to leave it alone. And tangent is the same as sine over cosine. Now, that's the substitution part, the math part. I'm going to put sine over 1 and multiply these two fractions together. So 1 over cosine has not changed. This becomes sine square over cosine. I now have a common denominator, so I can combine my fractions. 1 minus sine square theta over cosine. Now, I didn't start with a square, but I have a square. So now I can consider the Pythagorean identities. Well, the one that has sine squared in it, if you go back and look, is cosine square plus sine square equals to 1. Okay, that is a proven identity. All right, so what I can do with this identity is I can actually manipulate the identity to produce a substitution that is valid. I subtracted sine square from both sides. Now, what I'm going to do, because I manipulated this formula, this identity that has been proven, I'm going to take 1 minus sine square out and replace it with cosine square. So that gives me cosine square theta over cosine. And when you reduce that, that is no different than reducing an x squared over an x to an x. A cosine squared divided by a cosine is a cosine. So I did all of that to get one trig function. Now, keep in mind, if that were a cosine square as a final answer, that would be just fine. Not a problem. Okay? One trig function. Doesn't matter what the exponent is. Doesn't matter if it has a multiplier out in front of it. One trig function. That is your goal. Any questions about the first one? All right. Second one, I'm going to make the sine and cosine substitution for tangent. Tangent is equivalent. I'm going to leave the first two alone. Tangent is equivalent to sine over cosine. So I took tangent out and replaced it with its equivalent. What else is tangent equivalent to? There's one more thing on your list besides sine over cosine. Tangent's also equivalent to 1 over cotangent, okay? If you have a problem and it's got a whole bunch of other cotangents in it, take tangent out and put 1 over cotangent in its place. The reason I chose sines and cosines for this one is because I had a whole bunch of sines and cosines, okay? So if I put this over 1, do the math, that cancels. So I end up with sine A plus sine A, which is 2 sine A. That's just combining like terms at that point. 1 plus 1 is 2. No different than x plus x being 2x. All right. Now, there are a lot of ways that you can work the third problem. All right. I'm going to show you the quick and easy. Do you see squares? All right. Is there a Pythagorean identity that relates these two together? Pythagorean identity, top of the second page or either on your front page. What is it? Cotangent square x or theta plus 1 equals 2 cosecant square. So you have a direct relationship. Well, unfortunately, this says cotangent square minus cosecant square. Can I manipulate this somehow to where I can get it to equal cotangent square minus cosecant square? I can if I move that over by subtraction, but I have to move that over as well. Do y'all agree? So I'm going to subtract the cosecant, and at the same time, I'm going to move the 1 to the other side by subtracting. So cosecant square x minus cotangent square x minus cosecant square x, that equals -1. You're trying to get one trig function, one number. I just got one number. It's a negative number, I don't care, but it's a number. Okay, that's the quick way. Now, if you can't think of anything else to do, turn everything to sines and cosines. Well, cotangent is cosine square over sine square. I use the squares because my original function is squared. Then cosecant is the same as 1 over sine square. If you can't think of anything to do, start there first. Sometimes that will take you quick and easy, and sometimes it will take you going up to Ardmore, jumping on I-65 headed south, going to 565 and coming back east, and then ending up at Bridge Street. How many of you would go through Ardmore to get to Bridge Street? I didn't think so. But you know what? Sometimes when you do these problems, that's what it feels like, that you're going around the world to get to Bridge Street. Make sense? Okay. So here I have a common denominator. So I get cosine square u minus 1 all over my common denominator. I can grab my Pythagorean identity, cosine square plus sine square equals 1. I can manipulate that to be cosine square minus 1. That means I have to subtract the 1, but I have to move that to the other side as well. So cosine square x minus 1 equals to negative sine square x. So all of this is going to come out. I'm going to replace it with negative sine square u over sine square u, and I still get to my negative 1. Everybody okay with that? All right. Any thoughts on what we can do with number 4? I'm trying to show you some options because sometimes I do things that y'all would have never thought about on your own, but once I show it to you, when you start trying to work these on your own, you go, oh, I wonder if that works. Okay? Because I can't tell you every single time this is what you're going to do step by step. That's not how these works. They are humongous puzzles, and you've got to figure them out. All right, so here, one thing that you would never think about is I can rewrite this as sine x over cosine x times tangent x plus cotangent x over 1. Notice that I have a monomial denominator. If I were to multiply these back together, wouldn't I get sine times the parentheses on top and cosine on the bottom? So I can separate that. Sine over cosine always produces tangent. Since I have a lot of tangents, and this is kind of what I was alluding to just a few minutes ago, I'm actually going to take cotangent out and put 1 over tangent in its place, making a legitimate substitution. And now I'm going to distribute tangent all the way across. So that gives me tangent square x plus 1. Because tangent times 1 over tangent, the tangents would cancel. What does tangent square plus 1 Pythagorean identity equal to? Secant square x. That would be my one final trig function. Now, if you don't want to do that method, you can fall back on the tried and true. We're still going to get to secant square. May take us a little bit longer. Tried and true, when everything else fails, and sometimes you're going to start going down a path and you're going to go phew, and have to start over again. And that is okay until you get a little more comfortable with these. I'm going to change tangent and cotangent to sines and cosines. So I have sine x, that's going to be sine x over cosine, plus cosine x over sine. And all of that is still over cosine. Do y'all agree with that? I'm going to distribute the sine across the top. That gives me sine square x over cosine plus cosine. And all of that is still over cosine. Do you agree the sine x would cancel from there? Now, if I put that over 1 and create a common denominator, I would have to multiply this one by cosine x over cosine x to get that common denominator. Do y'all agree with that? So now I am at sine square x over cosine plus cosine square x over cosine. And all of that is over cosine. Still have not lost that original denominator. So I can add my fractions together. I get sine square x plus cosine square x all over cosine, all over cosine. Pythagorean identity says cosine square plus sine square is 1. So I end up with 1 over cosine divided by cosine. When I do the math, that's 1 over cosine multiplied by the reciprocal, 1 over cosine. Do you see how what I mean by going up to Ardmore to get to Bridge Street? Okay, so that gives me 1 over cosine square, which is the same as secant square. Same answer, a lot more work. Does that make sense? So sometimes, even though plugging in sines and cosines is a fallback, it's not always the most efficient use of your time. All right. Any suggestions for 5 and 6? All right, I'm going to show you without changing to sines and cosines. I'm going to put cosecant over 1, and I'm going to create a common denominator. So this would become cosecant square theta over cosecant minus cotangent square theta over cosecant theta. I now have a common denominator. That also puts some squares in my problem, so I can try to relate those back to a Pythagorean identity. And there is one that says cotangent square plus 1 is equal to cosecant square. Do y'all agree? So if I move this over, that gives me 1 equals to cosecant square x minus cotangent square x. What that does is it allows me to take that numerator out and replace it with a 1. And 1 over cosecant is equivalent to sine. So I did every bit of that without having to replace the sines and cosines. Can I do it by replacing sine and cosine? Yes. I can take each cosecant and put 1 over sine, and I can take cotangent square and put sine, or cosine squared over sine squared. All right. For number 6, I'm going to use it without making any substitutions. I have a monomial denominator, so I'm going to split this denominator. So that's going to be cosecant square over cosecant, or just cosecant over cosecant, minus sine of beta over cosecant beta. Okay, so that gives me 1 minus, I need to do a little bit of work over here. So I'm going to change that to sine. So that would be sine beta. So I'm going to take this over here. 1 over sine beta. When I take the numerator and multiply by the reciprocal of the denominator, multiply by that reciprocal, I get sine square. We've done this one before. That would be the cosine square beta plus sine square beta equals to 1. And if I move that over, I end up with cosine square equaling to 1 minus sine square. So that means 1 minus sine square is the same as cosine square. Any questions about that? All right, so on the next page, we're going to do things just a little bit funky. We're actually going to start at the bottom. Yes, ma'am. All right, so we're actually going to start with number 12 because these involve factoring and the top ones do not involve factoring. So we're going to work number 12, number 11. We're going to go completely backwards, then 10, then 9. We may or may not get to 7 and 8. But 7 and 8 will work out very similar to some of the other ones that we've done. So in this particular problem, I'm actually going to incorporate greatest common factor factoring. Okay, I have in that numerator two terms that have a sign cube. So I'm going to factor out greatest common factor, sign cube. That gives me cosecant square x minus 1 over cosine cube x. Now, I did this just a minute ago. Don't know how many of you were watching that, or we can actually take this. That is that cotangent square theta plus 1 equals to cosecant square. If I subtract 1, then cotangent square is equal to cosecant square minus 1, which means I can take this out and replace it with cotangent square. Oops. Y'all with me so far? So I did greatest common factor. I looked at this and I have a square. So I found my Pythagorean identity that involved the cosecant square and I made that substitution. All right, so here, since I have a whole bunch of monomials, I'm going to take cotangent square and turn it into cosine square over sine square. Y'all with me? So I took cotangent square out and replaced it with cosine square over sine square. Now, if I put sine cube over 1, that changes that to just sine x. So I have sine x times cosine square all over cosine to the third x. What do you think mathematically could happen here? What could cancel? Give you a hint. These two cosines, it's all multiplication and division, right? There's no addition, no subtraction. So these two cosines will knock that down to just cosine x. So now I am to sine x over cosine x, which is equivalent to tangent. Now, could you have gone about this a different way? Absolutely. I just wanted you to see a problem where factoring was involved. Is this the way second period went about it? Absolutely not. Okay, but I wanted to give you an example of factoring. Now, example 11 is a greatest common factor as well. What's the greatest common factor that we're going to factor out of the two sets of terms? That is correct. So when I do that, I have tangent square y, and that's 1 minus sine square. Now, we have done this one quite a bit. 1 minus sine square. What is that equivalent to? We have done this one probably 2 or 3 times already. Cosine square. So now I have a tangent square times a cosine square. So I'm going to turn this to sine square over cosine square, because that is a valid substitution. The cosine squares will cancel, and I am left with sine square. And that would be my one and only one function. Everybody okay with that? All right. Now, I know I said I was going to go backwards, but we're really going to do number 9 before we do number 10, because if we do number 9 first, number 10 will make a little more sense. Do you remember what these are called? Starts with a C, second letter's an O, third letter's an N. Conjugates. There you go. Yep. They are conjugates. And when you multiply conjugates together, you get a square minus b square. That could be in the form of x plus 2 times x minus 2. It could be 4 plus the square root of 3 times 4 minus the square root of 3. Conjugates come in any form, even trig identity form. So now that I've said conjugates here, do you see the conjugates in the numerator of number 9? Okay, so when you multiply those out, you're going to do a square minus, it's always minus b square. So that's going to be cosecant square x minus 1 over cosecant square x. Everybody with me so far? So I multiplied my conjugates out using my shortcut conjugate rule. And this is what I get. Now, there's a lot of things that I can do from right here. If I want to go all sines and cosines, I can put 1 over sine square and 1 over sine square in place of both of those and work from there. Okay, let's do that one, and then I'll show you the other way. So from this point, you have 2 options. Option number 1, 1 over sine square minus 1 over 1 minus sine square. I can take my numerator and I can multiply it by the reciprocal of the denominator, which is sine square x over 1. I'm multiplying by that reciprocal. When I distribute, what happens here? What's 1 over sine square times sine square over 1? 1. Negative 1 times sine square is negative sine square. And you just told me in the very last problem that this was equal to cosine square. Do y'all agree with that? All right. That's when all else fails and you want to do nothing but sines and cosines. Now for this one, the second way, once I get here, once I get rid of my conjugates, then I'm going to separate this fraction. I'm going to do cosecant square x over cosecant square x minus 1 over cosecant square. Cosecant square divided by itself is a 1. 1 over cosecant square is the same as sine square, and that will give me cosine square as well. So I have 2 options. You do one or the other. You do one or you do number 2. Do you think there could be a third option? Yes. Do you think there's possibly a fourth? Yes. But everything we've done is mathematically sound. So make your substitutions, do the math. All right? Now, I see part of a conjugate. I see a binomial right here. Anytime I have, and I'll do this every time, if I have a binomial denominator, I multiply by the conjugate to create a monomial denominator so that I can do stuff like I did over here. So I'm going to multiply this one fraction by one minus sign, the conjugate of that one plus sign. Now, poor little old tangent is sitting over here and I hadn't touched it yet. Now, across the top, I'm not actually going to distribute that. I'm going to leave it as cosine times the 1 minus sign. Resist the urge to distribute. I know you'll want to. And then on the bottom, we do a squared minus b squared. So 1 minus sine square. Now, for about the 5th time today, at least 4, possibly 5, what does 1 minus sine square end up being? Cosine square. If you don't know anything, you're going to know sine square plus cosine square is 1, and 1 minus sine square is cosine square. If nothing else, those are the formulas you'll walk away. So, I have my numerator and my 1 minus sine over my new denominator. This cosine will reduce that one down. Do y'all agree? So now I'm down to tangent theta plus 1 minus sine theta over cosine. I now have a monomial denominator, which will allow me to split this fraction. Watch what happens when you split the fraction. I get 1 over cosine minus sine over cosine. When I split that fraction, I get the 2 parts. Now, a couple of things you can do here, and I'm going to have to go back over here because I have written too big and I'm running out of space. So I'm going to take this bad boy this way. I can do one of 2 things. I can change tangent to sine over cosine, and it will cancel this sine over cosine, or I can change this to tangent. Which one do you want to do? Change sine cosine or change to tangent? Okay. So that gives me tangent theta plus, do you know what I'm going to do here? I'm going to go ahead and change that to secant theta minus tangent theta. The tangents will cancel each other out, and I am all the way to secant theta. Are there other ways that you could do this? Absolutely. Lots of different variations to the steps along the way. Everything you do has to be mathematically sound. And everything we did was mathematically sound. Substitutions have to be valid. Okay. Now, we probably have time for one more. Do you want to do number 7 or do you want to do number 8? Number 8. Number 8. Number 8. Why do you think I'm suggesting we do number 8? What kind of denominator does it have? Conjugate. Okay. Now, We're actually going to do this one just a little bit different. We're going to do Old Faithful, everything sines and cosines. Okay, so this is going to be sine alpha over cosine alpha, 1 over cosine alpha, and just cosine alpha. So I change tangent and secant. Now, before I can do anything else, I can't multiply by the reciprocal yet, but I'm going to create one fraction here. So I'm going to take this over here to my workspace. 1 over cosine alpha minus cosine alpha. If I put that over 1, I have to multiply top and bottom by cosine alpha to create a common denominator. Do y'all agree? All right, so this becomes 1 over cosine alpha minus cosine square alpha over cosine. That's what my denominator just became. I can go one step further. That's sine alpha over cosine alpha. And all of that is over, I'm still not done with this. That's 1 minus cosine square over cosine. What does 1 minus cosine square equal to? What does 1 minus cosine square over cosine equal to? If you take your cosine square plus sine square equals to 1, and I move that over, this time I get sine square equals to 1 minus cosine square alpha. Fish didn't come up. So that, my new numerator or denominator is sine square alpha cosine alpha. Fraction divided by fraction, you can flip and multiply. So sine alpha over cosine alpha times cosine over sine square. When everything cancels, I am at 1 over sine, which is cosecant. And that would be your final answer. Any questions about that one? It takes a lot of patience and a lot of practice with these. Now, what I plan on teaching on Monday is proving trig identities. So you need to watch the notes from Monday. So that will be in the week of December 14th. And then Thursday and Friday, when you guys and gals are back in here, we will do sum and difference. We may get to double angles. I don't know. That is my intention, is to end with the sum and difference, or half angles and multiple angles. All right, so the next 2 pages, proving trig identities, y'all will have to find the video and watch it. It'll be posted in Math Excel, in Schools PLP. And then when y'all come back in here, we will do the last 4 pages of the set.